All right, so today we are going to do a couple of things. We'll move from planar structures and the discussion of capacitance for parallel plate conductors to then cylindrical structures. And you will see how we are going to move from this particular cylindrical structure that has a charge inside to a two-conductor cylindrical geometry, which we will call the coaxial conductor, coaxial waveguide, or coaxial line. Now, there are a lot of other examples in parallel plate cases for capacitance, and I will give you homework on that. We're not going to do them all in class because they're all like repetitions of the same thing. So I'll give them to you as homework. So what we would like to do, there are two types of important geometries in electrostatics, at least for us that will try to understand electrostatics and magnetostatics and electromagnetics in the context of circuit theory and how we use these to do circuit design, because you know circuits, all right? You have seen them before. And then now it's time to relate those EM concepts to the circuits that you have seen and worked with. And understand why some of the particular expressions that you've seen in the past now make sense, all right, on the basis of what happens in these structures. Why these lines are important? Because a parallel plate line that has two conductors is the is what created the genesis, if you like, for all of the other types of lines that we use in microelectronics. One of them is the microstrip, the other is like a slot line, the other can be a strip line, I mean, the other is a coplanar line. All of these are lines that are made out of planar conductors in different arrangements. But the parallel plate conductor was the beginning, all right, of that group. Then the other one that created another group of transmission lines is the coaxial line. And the coaxial line started with two cylinders, conducting cylinders, one inside the other, all right? And then from there, we found the capacitance using electrostatics. The same thing applies to also parallel plate lines. Then we go to magnetostatics, we find the inductance, all right? And we do it with statics, both electrostatics for capacitance, magnetostatics for inductance, because it's easier to see them separately. And then we combine them together and we create then a which is the right thing to do for electromagnetics, all right, for waves that are both electric and magnetic, and they are coupled. Because capacitances and inductances, we are going to help us define a new concept for transmission lines, for interconnects, as we call them, which is called the characteristic impedance. Extremely important for circuit designs. And then from there, we're going to go to transmission lines, and we're going to see all kinds of things, how you match transmission lines, how you create matching circuits, how you create filters, for example, and all kinds of other stuff. And we're not going to do all of this, but then at least creates the foundation on which you can build more work through other classes to learn about receivers, how a receiver works, for example. All right, so this class has a theme. It's a story, all right? That's what you need to remember at the end, that story. It's all connected. There is all a reason for doing it. So now that we've done the parallel plate, now we go to this new class, which is, as I said, important. And before we go to what we call the coaxial conductor, coaxial means there are two metals, two conducting structures. Where is it? Here. Like the green ones, two conductors, cylinders. All right, one can be, I can use this one as an example. Think of this. Let's see. Assume that the outer is one conductor and the inner is another conductor. There are two like pipes, all right? Consider you have two pipes, one narrow one, one big one, and then you put the narrow inside the big one, and you create something like that. It looks like this exactly. Now, if you had an outside that you could see, the inside is hard paper, you can see. If the outside, assume that you had another one, that would be what we would call a coaxial line with a material in between. Because always those lines, to hold the conductors in the same distance, to hold them, to make them concentric, which means that you have the same axis, you have to have a material. Otherwise, you know, what is going to keep them in place? So either is a full material along the whole thing, or rods of material that are put periodically. Depends on how you want to design it. But it's like assume these two conductors, one the outside, one the inside. The inside can be hollow like this one, or it can be fully like filled like a metal, as you can see here in the picture. That is called a coaxial. Coaxial because they have the axis the same, all right? Coaxial conductors, coaxial waveguides. Before we go to that one, we are going to solve another problem in cylindrical, but this problem is not foreign to us in terms of a concept, all right? We just have to apply known concepts to a cylindrical geometry. We have seen these concepts in spheres, for example. Okay, what is now this problem? Here we have a cylinder, the blue one. It's a conducting cylinder, and you can see what I have at the side. What do I have on the side of the cylinder? Ground. Why do I have this ground? Because what we've seen is the following. If I have here, so let me also write, you can see what I'm writing. Okay. If I have here these charges, all right, inside, and in fact, let me add a page so I can draw. So here, add a page. Okay, I will eliminate the page. I will just, because everything is here, but I need to write. So let's assume this is the cross section of, this structure here that I showed you. So it looks like this. The outside conductor, all right? And let's assume that this is thick. So I will make it as thick as possible. And then the inside conductor. All right, and I will make that thick too. If I make it, okay, made it like that. Or let's assume that I forget for this for now. I put here a charge like ours, okay? And then the charge looks like this. The charge distributes on a fictional cylindrical surface evenly. There is nothing to hold it. You know, this is a theoretical problem, but there is a charge that distributes evenly on this coaxial cylindrical surface, coaxial with the outside. What is going to happen because of the positive charges in the metal? What is going to happen? What is going to happen in the metal because of these positive charges? Come on, we talked about this. It's Friday afternoon. There are going to be all of the electrons here, because in equilibrium, all right, without the charges and everything, the metal does not show any charges. All right, I mean, the electrons are mingling everywhere in between the atoms. They go like randomly left and right. They kick each other and everything, and that's the end of it. Nothing happens. If they're all randomized small movements at the end, it's all in equilibrium. There is no charge anywhere concentrating in any particular way. However, when these positive charges are here, all of the electrons see them, feel the force, as they say in some of these movies. They feel the force, and they all come and align on the inside surface of this conductor. So they will all align here, not in the air, on the surface of the conductor. That's how I can show them now. All right, just on the surface, all aligned. And how are they gonna align? Depends on how the charge inside the conductor is distributed. Because this charge inside the conductor is uniformly distributed on this fictitious surface, then the electrons will also distribute uniformly. What is gonna happen to those places, the holes that the electrons leave behind? Yes, they're gonna migrate to the outside, and how are they going to distribute? Evenly. Why is that? I mean, we know why the electrons will distribute evenly. But why will the holes distribute evenly here? You remember what we said? Yes, exactly. And so they don't see the electrons, number one. And then number two, the only thing they feel is the forces among themselves. It's like the elbows, all right? They have to be at some distance. They cannot be one next to the other. It's like they all go like that, for example. They were telling us in the beginning of the COVID, then you have to be 6 feet away. Personal space. Yes, personal space. Exactly. You need to remember the personal space for the charges. Okay, so that's why I put here in the previous picture, I put this ground. And what happened when I put this ground? As we said, do the holes move to the ground? No. What comes from the ground? The electrons, all right? Need to remember the following. And maybe it's gonna be easier if you understand a little bit the structure. So if I have a conductor, all right, the conductor, the structure is like a crystallic structure. It has a periodicity. And for those who have done some kind of metals, if you have any classes on metals, they all have this periodic three-dimensional structure, and that the nodes are all the atoms, and they stay there. Of course, they don't move. Atoms don't move. Otherwise, you're going to have a material that will be like water or something, you know? No, these are solids. So they stay. The electrons go around the atoms, but the electrons can move. All right? The electrons is like you have a small satellite around the atom. It can move. It can leave if there is not enough, especially the outer electrons. All right, like the outer ones, that they are slightly held by the electric force from the nucleus. Those can leave if there is an electric field. If they leave, what do they leave behind? An empty space. That's the hole. Holes do not move because the atoms do not move. A hole is part of the atom. What happens that seems like holes are moving is that another electron comes and takes the place of the previous one that left. And it seems like now this other electron that came and took this place left an empty spot somewhere else. And that's why it seems that the holes move. Holes do not move, only electrons. Therefore, the only thing can happen here is for electrons to come up here and neutralize all of these holes. All right, and therefore we like that. Why we like that? Because then we're not going to have anything to radiate outside, which is going to be a huge problem. And that's why when your TV set, if you have an older TV set, a not good connection, does not work and shows a lot of noise, check, first of all, the grounding of your cables before you try to do anything else to buy a new TV. All right, so in any case, that's why we had. So now we go and number one, it says, find the electric field intensity in regions. The one which is within that ring of charges, all right, or that cylinder of charges, inside that cylinder, it's region 1. So here, that is 1. And then 2 is here, between that cylinder of charges and the surface of the other cylinder that covers, that encloses this whole structure. All right, so that's number 1. Okay, how do we do this? We do something similar, even if we are in cylindrical coordinates. And you remember cylindrical coordinates have what? What are the 3 coordinates in a cylindrical coordinate system? A sub rho, A sub phi, and A sub z. And you can see them here, all right? A sub rho is along the radial direction. A sub z is along the z direction, and A sub phi at every point where you are sitting as an observer, your A sub rho is going to be along the radial direction, and your A sub phi is going to be perpendicular to A sub rho and going through you but on the plane, on the XY plane that would normally correspond to that. Okay, so that's how we define it. Now, in a problem where everything has a cylindrical symmetry, what do we know is happening? Let's assume that we have a cylinder like this. All of the charges are uniformly distributed, even if I have given a length, all right, here. I have given a length, but consider that length to be just a piece of an infinite cylinder that has all of these charges. So we don't have edge effects and stuff. We don't have what happens when it terminates somewhere, all right? Which we call them the edge effects. That's a different story. We're not going to touch this right now. Now we will assume that this L section is part of a longer cylinder that has all of these infinite charges that sit like on this cylindrical surface, imaginary surface, and then it's covered outside with a conductor, cylindrical conductor. So what we do is we go and find a surface, a cylindrical surface inside the charges, which is the green one. See, in 3D, you see like the green one here. I've drawn it for you to see it. And in 2D, because if I have a total cylindrical symmetry, first of all, it means that I have no Z dependence, all right? If it's a uniform charge, wherever I go, I will see the same thing. Wherever I go, I don't see anything different. It's like you go inside a tunnel, all right? And then there are no other cars. And then you go, you see the same thing. You don't know where you are. I mean, it's exactly the same kind of scenery, same kind of thing here. Along the Z direction, there is no change of anything because at every Z, I see the same kind of structure, I see the same kind of sources, charges. So we can move anywhere, so I can cut a cross section like this, and I can cut it wherever I want, all right? Because it's gonna always show me the same. Now, on the cross section, I also see that I have another kind of symmetry, which means however I move around, regardless of how big of an angle phi I create, all right, as I move around, as long as I am at the same distance from the axis of the cylinder, I see the same thing. So if I go and move around this green circle inside, I will see the same thing. If I go around this other green circle in region 2, I will see also the same thing. All right, so these are important symmetries to keep in mind. So now what do? I go inside the knife. I know that when I have these cylindrical symmetries, what can I use? Which of the two expressions for the electric field I'm going to use? Gauss's law. Remember we said that if you have a symmetry, all right, spherical symmetry, if you have a cylindrical symmetry, if you are like on an infinite plane with uniform charge everywhere, then we use Gauss's law because it's the easiest one to be incorporated in a solution and then give us a result. Coulomb's law, even if it's the derivative or like a relative to Gauss's law, it's more difficult to manage for these kinds. I mean, for any structure. So why going through Coulomb's law and having to go through a lot of calculations that involve multiple integrations, right? So we'll try to avoid that. Gauss's law says the following. Here is what I want you to remember. This charge here extends on a surface, right? It's only on a surface. So the total charge is going to be in coulombs, obviously. But what will the charge distribution be? Excuse me, the charge density. Yeah, the charge is going to distribute on a cylindrical surface. So if the total charge Q, capital Q, is in coulombs, what will a charge density be? What type of a density are we going to have? Is it going to be volume? Is it going to be surface? Is it going to be line? Surface, because the charge distributes on the surface. So Q sub S, while Q, total Q, will have the units of coulombs, Q sub S will have the units of coulombs per meter square. Okay? Now, just to keep it in mind. So we take here and we say, okay, we're going to take a volume, but we are going to, since Z is not important, we are going to take infinitesimally a volume, which is by infinitesimally thin, along the Z. It's like a slice. We take a thin slice of this cylindrical structure. And also, it's like a smaller cylinder inside the charge, and it's a slice. This is very small. So I go here and apply what I know, which is the divergence theorem. And the divergence theorem, it says that I can integrate my total charge over a volume. And now my volume is this green one that you see, the small. And that is going to translate into a closed surface, all right, integral, because any volume is enclosed by a closed surface. There is no volume that is enclosed by an open surface. There's no such a thing, all right? So total volume. And therefore, we go from this to this equation that involves a closed surface integral. Okay. What is the surface that is made, that is enclosing this green volume? What is how many components does this surface have? 3 that I can recognize. It has like this one. Okay, this one. Assume that the inner conductor is filled. How many? And assume that this is my volume. All right. So how many surfaces do I have? I have the top surface, which is flat, like a disc, is like a disc. Look at this. How would I call the whole thing? Anyway, it's like a whole circle, the whole thing. then another one, 2, and then the one surrounding it, 3. I have 3 surfaces, all right? Here I call them S1 is the top one, S2 is the one below, and S is the one that goes around, like a cylindrical surface. Now, you remember that surfaces have directions, all right? There's no surface without a direction. So what are the directions of the surfaces? We also said that the direction of a surface that encloses a volume is outwards from the volume. Remember that? As a convention, this is what we have agreed to do. So the direction of this surface here is N1 is the normal, the direction N1 for S1 up. N2 goes down for S2, all right? All of them outwards from the volume. And for S is N. So N1 is along the Z, positive Z direction. N2 is along the negative Z direction. And N is along the radial direction. All right, so now I know what the directions of those are. Okay. Because it's a cylindrical structure, and because it is independent of Z, whatever happens on the upper surface would be canceled out by the lower surface. Whatever happens on S1 will be canceled out, but whatever happens on S2. However, in this problem, just because there is no Z dependence, there is no Z coordinate. There is no Z component in D, all right? D does not have a Z component because all of the solutions will be independent of Z. It does not have a phi component because all of the solutions will be independent of phi. Therefore, D of Z and D sub Z, the derivative with respect to Z and the derivative with respect to phi will all be 0. So in this problem, there is only one component, which is the radial component, and it's going to have only one dependence on the radius, rho. Okay. So yes, they will cancel out, but also in this particular case, they are 0, each one of them. All right, this and these are 0. Now, this one, of course, is not 0 because we have the rho direction. And then the rho, which is along the rho direction, has to be integrated on this surface S. All right, and you see here, it's the inner product between 2 vectors. The vectors are along the same direction. So the inner product of the 2 unit vectors is 1. Remember that? If you have A, so here, we have said that one of the fundamental properties of unit vectors is that the inner product of a unit vector with itself is 1. That's very fundamental. And how much is the inner product of a unit vector with one of the others in the system? 0. Because all of the unit vectors of every coordinate system are perpendicular with each other. So it's only with itself. Now, and we said is along the rho direction. So this inner product here gives 1, according to what I wrote down there. And therefore, you have here that this surface integral will be the surface integral of d rho on this surface that I have here, the outside of the green. And therefore, since d sub rho is constant on this surface because all of the points have the same distance from the axis, therefore I get this value out and I multiply, I find that the surface here that finally I integrate is 2 pi rho times dz. Okay? And that is equal, according to this, which is Gauss's law, this volume integral here, which I have not touched it yet, it would practically lead to the volume integral of whatever charge is enclosed by this volume. But how much charge is enclosed by this volume? Zero, because all of the charge is outside. All right. So that volume integral is zero, which implies what? That because these two are equal, it implies that this above equals zero. Now, this is the proof of something that we have said. You remember? We have said in any problem, that if you integrate over a volume that does not include charges, if you integrate the electric field or the electric flux density over a volume that does not include any charges, what happens to that integral? Is zero. All right, so if I have a charge here, even if a charge that creates an electric field, but I integrate on a volume that does not include this charge, this integral is always zero. If I integrate the electric field on a volume that does not include this charge, that integral is zero. Which means, in other words, whatever field lines are going through the volume, they go out. It's like a fluid, all right? It's like you have a hose with water. Whatever water comes in is going to go out, unless you have a spring somewhere, all right? That creates, like our sources is like a spring. There are sources that create energy, and there are other places that are called them sinks. Okay, all of the sources create an electromagnetic field, therefore create electric energy in our particular case. All right, so it's like a spring that brings new water. If you don't have a spring and there is water that comes down, and then you try to find out what is the total amount of water in a closed volume, it's zero, because whatever comes in, it goes out. All right, it does not go anywhere else in your hose. Otherwise, only if there is a hole and the water goes out from the hole. But if you have the same kind of problem here, if you have a charge here and you're looking at the field somewhere else and you integrate that field on a closed volume, it's zero, because whatever field lines come in, the same number of field lines go out. All right. So on the basis of that, I did not have to prove anything. I just could say is zero. So now you're going to remember that. All right. Also, we have seen this before in the sphere. What did we say about the sphere? That if you are inside the charges and your charges are behind you and you integrate there, your field is zero. Why? Because the charges cancel each other's effect. When you're inside, when they like create either a cylindrical surface or a sphere. The same thing would apply if I had a cube with charges uniformly and I was inside the cube. What would I see? Would I see an electric field if I had uniformly, I have a cube, I'm inside. And then I have charges everywhere around me on the surface of the cube. And then I'm trying to get a voltmeter and measure a voltage, which is like electric field, all right? What would I measure? Zero, only the noise of my equipment, because all they cancel each other. Okay, let's now consider getting another, going to now volume 2, or like region 2. Region 2, so we found that inside the charges, the field is zero. However, now let's see what happens between the charges and the conductor. We'll follow exactly the same approach, But there is one only difference. And the difference is that as I integrate, all right, now here, of course, I eliminated this at Z, which is fine. I mean, you can reduce it in this form, but as I integrate it, I start with a volume integral, obviously, in the beginning. And as I integrate here, I have already reduced the dimensions. That's why you see that. Whatever I integrate inside the volume, it gives me the charge. All right, so if I were to rewrite that, if you like, if I were to rewrite it, so follow the same, okay? So let's assume, let's do that because it may confuse you to be 2D. So what I will do here is, that is a volume, forget about that for a second, volume. And here, I have surface integral. Let me erase that too. Surface, okay, of D dot ds. Okay. Let me, in fact, do that. I will rewrite them, no problem. I just want to make sure that we don't. So, okay, volume. The volume we said is, is the volume integral of divergence of D dot dV is according to Gauss's law that says that the divergence of D is Q sub S. So the volume integral of Q sub S dV, first of all, so this will be equal. Q sub S is a surface, all right? So it's going to be the total surface density times the area of the surface on which it's distributed, which is going to be 2 pi rho times dz. Do you agree? Okay. That is on the left-hand side. So now, on the right-hand side of the equation, what do I have? I have like before. I have 3 integrations, S1, S2, and S and S. Okay, and so I can erase that for a second. Let me see. All right, as we said before, this is 0 because there is no dependency on, there is no direct, the only component that exists. There is no dependency on Z, there is no dependency on phi. There is of course only one component, which is D sub rho, and is a function of rho. Therefore, this is going to go to 0 because that implies the Z direction of D. We don't have a D sub Z. That goes to 0 because also implies that the only way to find a solution to that would be if D had a Z component. And this one here is going to be equal to D rho, which is constant on the surface, times the surface, which is going to be 2 pi rho dz. Okay? So if I now take this one here and this one here, what did I do? There is a problem. Let me see. Okay. I know what the problem is. This is B, okay, because it's only on the B surface. All right, it's not on any surface. It's only on the surface that has a radius B. Okay, so if I equate these two, what do I find? I find exactly this. So let me write it. It's gonna be that D sub rho, which is here. I'll erase that. Erase this. I'll rewrite it. Is D sub rho equals Q sub S, and then I have 2 pi B D sub Z divided by 2 pi rho D sub Z. But I need, it's a 2 pi B D sub Z, and then the other is 2 pi D sub rho. It's kind of problematic. Oh no, it's not problematic, it's correct. So this one's problematic. Okay, so here, this, and this and that, and therefore D sub rho becomes equal to Q sub S over rho times B, which means that E sub rho is gonna be Q sub S times B divided by epsilon naught rho, okay? Which is in fact exactly what you found here. So from here, we found exactly the solution down there. And then you can plug in the numbers, and then you find exactly how much the field is. So here is the solution for that. Now, yes. From which? B is up here.
Well, when you scroll down, it said we have the same solution. But
here. Here.
The charge divided by epsilon naught divided by E.
Is that you mean B? Did I, unless I missed the B somewhere when I plugged it?
Oh, okay. Never mind, I see.
Yeah, there is a B. So I will check it out before I put them on the web. Make sure that I have not missed anything. Now, in this particular one, look what the question was. Assume that the outer surface of the cylindrical conductor is not grounded, all right? And find the field in region 3. So if it's not grounded, we said that you're going to have all of these positive charges. The positive charges are going to distribute evenly. And if I now create a surface like I did in the first part of this problem, if now my surface is all outside here, from the outside, the only charges that I will see are the positive charges, because the inside is separated from the outside by a perfect conductor, which is like the red and the white shirts. You put them into different rooms, they don't know what is happening. All right, so the charges outside separated by conductor that includes all of encloses all of the charges inside, they have no idea the charges what each other is doing. There is no coupling, there is no connection between them. They don't see each other because the field in the conductor is 0. The field of the charges inside does not go through the conductor. It stops inside. So the outside charges do not feel the force of the inside charges, all right? So in this case, we do solve exactly the same problem, and what we find is that the electric field outside is gonna be, this is so amazing, it's gonna be, for this uniform distribution, the same as if the conductor were not there. Look at the expression, is identical. And that's why if you put a metallic conductor here to isolate the inside from the outside, and you forget to ground it, it's like you don't have it. It's like it's not there, all right, from the outside. All right, so what happens if all of the charges inside were not uniformly distributed like that, but they were all, the whole charge Q was like in one place only. So for example, the question that I have for you is, what would happen if I had this problem? The same like before, all right, the cylinder, like this, but the cylinder uniform and everything, but the charges would be somewhere off. The cylinder of the charges will not be concentric, coaxial, will not have the same axis. So if I had to write a cross section, inside the cylinder of the charges will be like this. Okay, and then this one would still be thick. Conductor. What do you think would happen in this case? About the field inside and the field outside. Let's think a few minutes. Because let's assume that I wanted to say, find the outside field, the same, I have here a conductor, and let me make it thicker. So this one is like a thick conductor, and inside I have charges. And the charges distribute on this surface. And they're all positive, as before. Positive charges. What happens? Inside, what happens? First of all, let's find out what happens inside. What do you think? Where are the negative electrons? Where would they go? They will try to concentrate closest. You remember, the electrons are feeling a force that attracts them to the positive charges. So they are gonna go as close to them as possible, all right? And as a matter of fact, if the inside was also a conductor, the positive charges would come closest to the electrons. So if the charge inside was distributed on a conductor, also a conductor, all right? Then, you know what would happen? The moment I put charges in the inside conductor, they will not stay like that. What is gonna happen is the following. The positive charges and the negative will come as close as possible. All right, as close as possible, exactly. So here, the negative electrons will come here and will concentrate, and the positive charges will come here. Okay, so now I have to solve that problem. I can tell you how it's gonna look, but I cannot tell you exactly how it's gonna be in value. But if I were to ask you, so now that you have these, show me the electric field lines, how they go. How would you do them? Knowing that all of the electrons are crowded close to the holes, then I can say my electric lines, field lines, will go like this. and then here. All right. There will be weaker outside. Something like that. All right. Now, to find them, you have to use, in this particular case, you cannot use Gauss's law. You will have to use Coulomb's law to find them. But in any case, how about the outside? Yes, the outside will still be equally distributed because they do not know those charges, what is going on inside. All right, they don't know whether they have changed, the charges have changed their positions or anything like that. So the outside will look like this. It's not going to change as before. You will be exactly the same identical problem as you had before, even if the inside now looks totally different. All right. So this is just by thinking, so you can put all of this picture down without necessarily solving the equations. After you do that, then you can sit down and try to solve something. Now, the other thing, if your structure is uniform along the z direction, you will not have a z dependence, but you're going to have a phi dependence here. All right, so you're going to have two coordinates that you have to deal with inside. The inside problem, you will need to solve it with two coordinates, phi and rho. Because the electric field lines will have two components, phi and rho. But the outside is like the previous problem, it's going to have only rho. Will be straight lines out. Okay? Any questions? Now, I'll give you problems using these fundamentals, but in the problems, I'm not going to give you that because you cannot solve it unless you go into the computer. But I will give you problems where it's the same kind of symmetry, but with different materials inside. And in that case, you will have to think also of the boundary conditions as you go between air and the electric. Because here in the previous problem, if I had a dielectric in here, because D has only one direction, D rho has only one along the rho direction, which is going to be perpendicular to whatever cylindrical material you have, that is going to be continuous. I will remind that to you next week, but I will give you some problems like that. Some with dielectrics in plate parallel conductors and some with dielectrics in this. Okay. Any particular questions? Do you understand this material? At least physically, from the physics point of view? Okay, thank you. No quiz for Monday. Focus on your homework.